A handrail runs alongside a stairway. As the horizontal distance from the bottom of the stairway changes, the height of the handrail changes. Show that the relationship is linear, and then find the equation for the relationship. So this problem's asking us to do two things. Thing number one, is it linear? And thing number two, write the linear equation. So to tell if something is linear, that can mean one of two things. It means, is the rate of change between all of the points constant? Meaning, does it have a constant slope? If it does have a constant slope, what that means is if we graphed it, the graph would look like a completely straight line. So we can solve this, we can answer this question either way. We can use all of these points and find out, is the slope constant between all of these points? Or we can see, do all of these points form a straight line? Obviously, the easiest way to do this is, do they form a straight line? Since we've already got the graph, meaning, can I draw a straight line with a ruler that goes through all of these points? And you can see if I put my ruler up against these points, very clearly, yes, a straight line would go through all of these points just like that. So yes, this is a linear relationship because a straight line can be drawn through all of the points. So we've already answered the first question. The relationship is linear, and we don't want to leave it like that. We don't want to just say, yes, it's linear. The relationship is linear, but how do we know? The relationship is linear because all coordinate pairs let's say fall on the same line. There are probably a lot of good ways to word that, but I'm just going to say they all fall on the same line. Or a single linear equation includes all coordinate pairs, something like that. Okay, so the second part of the question says, find the equation for the relationship. Again, there are several ways to do this, but the way that we've been doing forever and ever is slope-intercept form is the way we write a linear relationship. There's more than just slope-intercept form to write it. We'll learn about some of those later, but for now, slope-intercept forms are our go-to. Slope-intercept form, as we know, requires us to find the slope and the y-intercept. It'd be really nice if this graph gave us the y-intercept. Now, when we connected our dots, we got a pretty good estimate of about where the y-intercept would be. If we zoom in there, it looks like maybe about 2.5 is where the y-intercept would be. Now you'll notice when I connected my dots, I actually connected my line, unfortunately, slightly below my dots. I didn't get exactly on the dots when I drew the line. So it may be a little higher than 2.5, like maybe 3.5, something like that. But that's a reasonable estimate for the y-intercept. Of course, I don't want to write my answer with an estimate. I want to know exactly what it is, but I'm expecting my answer to be maybe 2.5 to 3.5, somewhere in there. Let's start with the slope though, and define slope when I've got a set of points. All I need to do is just pick any two of those points and find what the change in y over the change in x is. And we have learned previously that a really easy, short way to write that is that m is equal to the change in y, which we can write as delta y, over the change in x, delta x. So what's y changing by and what is x changing by? We can use any 2 points we like. Now you may be thinking to yourself, well, if we've got the graph, why don't we just count rise over run? And counting rise over run would be excellent if we had 2 points that were exactly on an intersection of the grid. Unfortunately, the only one we seem to have that's exactly on the intersection is this 15, 15, and all the rest of them are kind of in the middle. Like we've got 10, 11, which is not right on the intersection, 5, 7. The 5 is right on the 5 line, but the 7 is not. It looks like it's a little below that line right there. None of these points really are exactly on the intersection of a grid line except for 15, 15. So just counting is not an option for us here, but that's okay. We can just pick 2 points. Any 2 points will work to find the slope. And as usual, if we're allowed to pick any 2 points that we want, we generally want to pick the ones that are easiest to work with. And when I say easiest, I mean if there are fractions or decimals that we can avoid, we want to do that. If we can avoid negatives, let's do that. In this case, there aren't any fractions, decimals, or negatives for us to worry about. All of the numbers that are here are whole numbers. So let's just pick the two smallest ones. And our two smallest coordinate pairs are 5, 7 and 10, 11. So our two y coordinates here are 7 and 11. So let's go ahead and subtract those to find the change in y. And our two x coordinates are 10 and 5. So we'll go ahead and subtract those to find the change in x. So the y changes by 3 and the x changes, I'm sorry, I cannot subtract here. The y changes by 4. 11 minus 7 is 4, kids, not 3. 4. And 10 minus 5 is 5. So our slope is 4/5. It's fine to leave it as 4/5. If you prefer decimals, you could do 4 divided by 5 and get 0.8. Doesn't matter. So now we know what the slope is. Let's go ahead and find the y-intercept. So let's go ahead and make sure we've got this boxed in or highlighted or something so we know where to find that when we come back to it. Let's find the y-intercept, which is b. So we go back to our y equals mx plus b. And I feel like we've done this about 1,000 times at this point. But we're going to plug in m, x, and y and solve for b. Now we know what m is because we just figured it out. M is 4/5 or 0.8 if you prefer using decimals. And then we need an x and a y. So we can use any x and any y that we want to from our graph up here. Any of those xy coordinate pairs are fine. And just like before, if we can pick whatever we want, let's pick the easiest pair to work with, which I'm going to use 5, 7. Whole numbers, and they're the smallest. So I'm going to use 5, 7 as my xy coordinate pair. I'm going to go ahead and switch the color here just so it's easy to tell them apart. Let's use 5 for x and 7 for y. Let's actually even do the y in a different color, just so that whenever I write this, it's easy to tell where we're doing the substitution. Okay, so I'm going to do my x in blue and my y in red. Okay, so I'm going to do y equals mx plus b. The y is going to be substituted with a 7. My m is going to be substituted with 4/5. X will be substituted with 5. And then on the end, plus b. And now all that we really need to do is just solve for b. So whether you used 4/5 or 0.8 for your m, the math is going to be the same. You can use a calculator if you like. 4/5 times 5 I think is really easy because the 5s will cancel out and leave us with just 4. You get the same thing if you do 0.8 times 5, of course, it's going to be 4. So we have 7 equals, and then 4/5 times 5 is just going to be 4. Let's go ahead and do that in yellow, I think. Just keep our color scheme as consistent as possible. Plus b. So 4 plus what is 7? Of course, the answer is 3. 4 plus 3 is 7. So we know that b is 3, but if you can't just look at this and tell, we can subtract 4 on both sides to get the answer for sure. 7 minus 4 is 3. So b equals 3. Which we were kind of expecting. Remember we said we thought our b was going to be somewhere about 2.5 to 3.5, and it's right in the middle, it's at 3. So our slope was 4/5 or 0.8, and our b is 3. So I'm going to write my answer as y equals 4/5 x plus 3, just because I like fractions in general, but it's totally fine and 100% correct to write it with the decimal slope as well. We're totally fine with decimals. Either one of those is a fantastic answer, either with the fraction or the decimal. 4/5 and 0.8 are the exact same number, so whichever one you like, they're both correct.